Bismillahirrahmanirrahim. In this course module, we will talk about vector spaces, subspaces, and dimension of subspace. So let's start with the definition of vector spaces. We take a set of vectors V, and we take two operators, which is one is addition and the other is multiplication. So addition is that takes two vectors from the set V, and multiplication operator is defined by multiplying an element from the set V with a scalar alpha. So we say this set of vectors V is a vector space if we take three members of the V, U, V, W, and we take two scalars A, B that belongs to a set of real numbers. If the following axioms hold, we say V is a vector space. So let's talk about these axioms. The first axiom is that V is closed under addition. So U plus, you take two members U, V that in V, and U plus V also belongs to V. Second axiom, that addition of two vectors is commutative. So U plus V plus W is equal to V plus bracket U plus W. So that means addition is associative. So there exists a 0 in the vector space. There's an element in the vector space V which you add to another vector V, you get the same vector V. Right? So 0 is identity with respect to addition. There exists minus U for every U in the vector space, such that when you add U to minus U, what you get is 0 identity element. Right? So these were the 5 axioms with respect to addition. Now let's talk about 5 more axioms. So A is a scalar. You multiply a vector with a scalar, you remain in the space in the set V. So if AU belongs to V. So seventh axiom, so multiplication of a scalar with a addition of vectors is equal to when you scale first and then followed by the addition. The eighth axiom would be A plus B into U is equal to AU plus BU. So we have addition of scalar numbers first and then multiplication with a vector is equivalent to if you scale vectors by scalars and then you add those two vectors. So ninth axiom would be AB times U, that would be equivalent to as ABU. So multiplication by scalars is associative. So or 1 times U as U. So there's an identity element 1, you multiply by a vector, you get the same vector. So if you have a set of vectors V and two operators addition, multiplication, addition of two vectors, multiplication by a scalar, and these 10 axioms hold for any such set V, we say V is a vector space. So before we talk about some examples of vector space, so let's look at the concept of a subspace. Let's look at the definition first. So we say we have a vector space V, and we take a subset of V and we denote it with W. So if W is also a vector space under addition and scalar multiplication that is defined on V, then we say that W is a subspace. Let's look at one more alternative definition to understand it more clearly. So we say W, which is a subset of V, is a subspace if, so we have a 0 element in W. W is closed under addition, as you take two vectors U, V in W, and U plus V also belongs to W. And W is closed under scalar multiplication that is defined on V. So we take a scalar A that belongs to R, and we take U that belongs to W. If AU also belongs to W, we say W is closed under scalar multiplication. So if these three properties hold, so for W we say W is a subspace. So there are special names to these three properties. The first one is non-emptiness, and the second and third are closure under addition and multiplication respectively. So in fact, every vector space V has at least two trivial subspaces. The first one is and the subspace that only contains 0, and the second one is the vector space itself. Say if you have a vector space V, so we say this vector space has two subspaces, and the first one is that only contains 0. This is a subspace, and the second is the vector space itself V, since it is by definition a subspace. And since in this course we are talking about standard set of real numbers, so we say in fact any R2, R1, R3, or in fact Rn. So all of these are vector spaces, or we say R2 is a subspace of R3 and R is a subspace R4, and so on and so forth. Right, so these are just very trivial examples. So let's look at a couple of more examples to understand the notion of subspace. Given some sets, we want to find out whether these sets represent a subspace or not. So we take a line through origin. So say we are in some higher dimensional space Rn, that could be n could be 50 or 100. So we have a line that is passing through origin. So this line contains 0. This line is closed under addition. So if you take 2 points on this line and you add those 2 points, you stay on the line. This line is closed under scalar multiplication. So we can say this line represents a subspace. So let's take one more example. Line that is not passing through origin. So this line is not a subspace because it does not contain 0. So 0 has to be part of the line. Or you can say if you take any point and multiply by 0, you get 0. And since 0 is not part of the set, we say this line is not a subspace. What about this set? A plane through origin. So this is in fact a subspace. What about this set? The first quadrant. So if you take this black vector and you scale it by negative value, you get this red vector. So red vector is not part of set. So this does not satisfy scaling property, and therefore this set first quadrant is not a subspace. What about this? A union of line and plane. So we say line is a subspace. We said plane is a subspace. What about union of line and plane? Obviously, this is not a subspace because we take these two vectors, that's on the line, and this black vector is on the plane. So you get this red vector, which is not part of the set. So we say therefore this is not a subspace. Okay, let's look at two more examples. Work out those two. So we say we have a set W that consists of points x, y, and R2 in which x greater than or equal to 0. So what does this set represent? The first quadrant and the fourth quadrant in R2. So is this a subspace? So it does not satisfy the scaling property. Right? So this is not a subspace. What about part B, in which we have W that take all points from R3 of the form 0, x2, x3. So what does this set represent? So this set represents a two-dimensional plane along x2 and x3. This is in fact a subspace of R3, right? Because it satisfies all three properties. It contains 0, it is closed under addition, and it is closed under scalar multiplication. So this is a subspace. Let's also talk about the concept of dimension of subspace. So we say the number of vectors in any basis of V is called the dimension of V. So any vector space V, any subspace V, the dimension of V is given by the number of vectors in any basis of V. So what we know that a non-zero subspace has infinitely many different bases, but they all contain the same number of linearly independent vectors that are known as bases. So the number of vectors in any basis of V is called dimension of V. and we express dimension of V as dimV, or dimension of bracket V. So a couple of examples. If you have a line through origin in R4, so what is the dimension of this subspace? The dimension of subspace is 1. What's the dimension of the plane through origin in R3? The dimension of this subspace is 2, because it is a two-dimensional plane in R3. So this plane can have infinite number of bases, right? So any two vectors, they're not linearly dependent in the plane, represent bases for this plane, but the number of linearly independent vectors is always 2, and therefore this plane has 2 bases. The dimension of the dimension of this subspace is 2. Okay, so we stop here. In today's module we have talked about vector spaces, subspaces, examples of subspaces, and dimension of subspace. We'll continue in the next module. Thank you very much.